Let us look at the user inputs for setting up the plain orifice atomizer injections. First user input is position. As you can see here in the set injection properties panel, we have selected injection type as plain orifice atomizer. Then we input the number of particle streams. Within the point properties tab, we give all the properties associated with the plain orifice atomizer injections. First, position, we give the x, y, z coordinates of the injected stream. Next is the axis. Again, we give the x, y, z components of the vector defining the axis of the orifice. Next input is temperature, which is the temperature of the streams, that is the particle streams. Again, next input is mass flow rate. This is the mass flow rate of the streams coming out of the atomizer. Next is the vapor pressure, which is given in pascals. This is the vapor pressure governing the flow through the internal orifice. Next input is diameter, which is the diameter of the orifice, that is the injector inner diameter. Next input is orifice length. Then we also give the radius of curvature. This is the radius of curvature of the inlet corner. Next is the nozzle parameter. This is a constant for the spray angle correlation, which is given here in front of constant A. Next inputs are the azimuthal angles. For 3D sectors, we set the azimuthal start angle and the azimuthal stop angle. In case we are solving unsteady problem, we also give the starting and the end time for injection. Let us now see the user inputs for pressure swirl atomizer injections. The properties here are similar to the plain orifice atomizer. We need the position, axis, temperature, mass flow rate and injector inner diameter as well as azimuthal angles. We also need the spray angle, which is the spray angle of the injected stream. We need to input the absolute pressure upstream of the injection. Then the next input is sheet breakup. This is the value of the empirical constant that determines the length of the ligaments that are formed after sheet breakup. Then we have the other similar inputs to the earlier injections like the ligament diameter and the dispersion angle. Next type of injection is the air blast type of injection. Here, the first input is the outer diameter. This is the outer diameter of the injector. Next, we need the spray angle, which is the initial trajectory of the film as it leaves the end of the orifice. We also need to input the relative velocity, which is the maximum relative velocity that is produced by the sheet and air. Other inputs are sheet breakup, ligament diameter and dispersion angle as discussed earlier. All this has to be input in this particular section. Next type is the flat fan atomizer, which is similar to the pressure swirl atomizer, but there is a difference in the sense that it makes a flat sheet and does not use swirl. The liquid emerges from a wide, thin orifice as a flat liquid sheet that breaks up into droplets. Fan is assumed to originate from a virtual origin. User needs to input location of this origin. As shown here, this is the pictorial representation of how this model works. This is the virtual origin from which it is assumed that the fan originates. User inputs have to be given here, and we will discuss the user inputs one by one. Let us see the user inputs for the flat fan atomizer injection. First is the arc position. This specifies the coordinates of the center point of the arc from which the fan originates in the x center, y center and z center fields. This is to be input here in this particular section. Then we have the virtual position, which are coordinates of the virtual origin of the fan in the x virtual origin, y virtual origin and z virtual origin fields. After this, we have the normal vector, which will set the direction that is normal to the fan in the x fan normal, y fan normal and z fan normal vector fields. So in this way, we are defining the arc position, the virtual origin position and the normal vector position or location, as well as direction. Temperature, which is the temperature of the stream, is also specified in the temperature field. Mass flow rate, which will set the mass flow rate for the stream, is in the atomizer is specified in the flow rate field. Duration of injection is the next input, which is for unsteady particle tracking, and this will set the starting and the ending time of the injection in the start time and the stop time fields. Then we have the spray half angle, which will set the initial half angle of the drops as they leave the end of the orifice. Next we have the orifice width, which will set the width of the orifice in the orifice width field. A sheet breakup is the next input. This will set the value of the empirical constant that determines the length of the ligaments that are formed after sheet breakup. Next input is the dispersion angle. For smooth distribution of droplets, the initial velocities is varied within this dispersion angle. Next type of injection is the effervescent atomizer injection. Effervescent atomizer is the injection of liquid infused with superheated liquid or propellant. As the volatile liquid exits the nozzle, it rapidly changes phase. This phase change quickly breaks up the stream into small droplets with a wide dispersion angle. Model relies on rough empirical fits. The model panel is shown here. We will not go into much detail of this injection within this course. If anybody needs more information on this, they can ask us, and we will let you know more information during your course. In the end, we will see the file injection type. Here we give injection file as input, in which we specify all injections with their x, y, z coordinate and their u, v, w velocities. All parameters are in SI unit. We hook the user defined injection through file in this particular panel. Let us quickly review the drag modeling in particle models. Drag force is included within particle force balance. The force is given by this particular equation. These configurations are available. There is the Morsi-Alexander, the high Mach number effects, the Hadel-Levit-Spiel for non-spherical particles, and the Stokes law with Cunningham correction, which is for submicron particles. There are also chance of collision, that is particle collision, when particulate flow is taking place. Drag force is included within particle force balance. How does Fluent include collision calculations? Each droplet has possible collision partner. Let us say if n droplets or particles are there, then it has a chance of colliding with n-1 particles. Number of possible collision pair is approximately half n square. Droplet collision is modeled using two principles. Concept of parcels and O'Rourke method of stochastic estimate of collisions is used. O'Rourke algorithm assumes that two droplets may collide only if they are in the same continuous phase cell. So this concept is the rule that is used for modeling collisions. Probability of collision depends on particle velocity and diameter. The outcome tends to be coalescence if the particle collide head-on and bouncing if the collision is more oblique. In the end of this lesson, we will see boundary conditions applicable to DPM. First, we will see the reflect boundary condition. When we use reflect boundary condition, the particle will rebound from the boundary with a change in its momentum as defined by the coefficient of restitution. A normal or tangential coefficient of restitution equal to 1 means that the particle retains all of its momentum, that is in normal or tangential direction, after the rebound. This means it is an elastic collision. A normal or tangential coefficient of restitution equal to 0 means that the particle retains none of its normal or tangential momentum after the rebound. Next we have the trap boundary condition for particles. In this, the trajectory calculations are terminated and the fate of the particle is recorded as trapped. In case of evaporating droplets, their entire mass instantaneously passes into vapor phase and enters the cell adjacent to the boundary. The panel of the trap boundary condition is shown here. This is the pictorial representation of how the trap boundary condition works. Next is escape boundary condition. The particle is reported as having escaped when it encounters the boundary in question. Trajectory calculations are terminated at this particular location. This is the panel where we input the escape boundary condition. Now we will quickly see other types of boundary condition. First is wall jet. The wall jet type boundary condition is appropriate for high temperature walls where no significant liquid film is formed. The model is not appropriate for regimes where film is important. For example, cases like port fuel injection in SI engines, rainwater runoff, and many such similar cases. Next we have the wall film boundary condition. This boundary condition consists of 4 regimes: stick, rebound, spread and splash, which are based on the impact energy and wall temperature. Then we have the interior boundary condition. This boundary condition means that the particle will pass through the internal boundary. This option is available only for internal boundary zones such as radiator or porous jump. It is also possible to use a user-defined function to compute the behavior of particles at the physical boundary. For this we use UDFs. So now we are coming to the end of this DPM video lecture. We studied what DPM is in this particular lecture. We also saw the entire modeling setup of DPM. We also discussed different types of user inputs for DPM models like injection, drag laws and boundary conditions and how to specify them. It is recommended that you practice the standard answers tutorials on DPM as well as you complete the assignments in this course related to DPM.